So it's going to be kind of it's going to feel like going back to close to the beginning of the semester when we were focusing on design. So I showed this slide like the first or second lecture or something. How do we walk through designing a relational database? You know, basic, kind of similar to how do we design a program? You know, what are the requirements? Think about how to start forming it into code and algorithms and stuff. So started with conceptual design, and then we so that includes like the relational model, ER model, and everything. And then we kind of just skipped over this schema refinement part. And we've talked about physical design, you know, indexes and disk layout and stuff like that. We didn't actually skip number 3. We've been talking about it the whole time, but never really in a formal way. So you'll see what I mean by that. But it comes down to like more guarantees about consistency and something called normalization. So remember from way back in the beginning, one of the things we were trying to avoid in schema design is redundancy. So I asked the question, like, if we were trying to build a library, how do we represent a person checking out more than one book? And one of the options is maybe just, if they're all in one big table like this, you'd have to just put in multiple rows, including 3 copies of Malfoy and his phone number and his card number and everything. Kind of another way to phrase this issue is, what if the same book is checked out by multiple people, or if you have multiple copies of the book? And obviously this is not what we do. This redundancy is bad for the obvious reason, which is storage, but very bad in even more important ways, which is, now I have all this duplicated data. What if I change Malfoy's name? I have to go and find everywhere where that exists and change it in a lot of places. But let's look at maybe a different approach. So this is back to an LMS instead of a library. This is a modified version of what I've been showing, and this is not, hopefully not, the way you've designed your tables. So I have students and enrolled, but I've added name. I've copied name into enrolled. The reason you might want to do that is, now if you had a common query, if one of your common queries was give me the names of all people in a certain class, now you can do that without a join, right? So if enrolled did not have this name column, I could still do it, but I'd have to join these 2 tables on UID. You know, so maybe that does speed it up, but actually not really. If you have proper index on these tables, then the join is basically free. It's not actually turning into like an n² multiply here. And we've seen that. We've been looking at joins and indexes and the plan generator a lot lately. So no, definitely don't add a name column to the enrolled table just because you want to speed up one particular query. So why not? The basic problem, which I already mentioned, is duplicate storage. You don't want to have a whole bunch of the same name everywhere. The bigger problem is more of a design problem, because it introduces what are called update, insert, or deletion anomalies. So anytime I do an update or an insert or a deletion, those are now non-trivial. As an example of this, let's say that Harry decides to change his name to Harold to be more professional or something. Then we'd have to also go and change his name anywhere he's enrolled in a class. So we'd have to go write some other query that finds all of his enrollments and updates it there. And what if we did this again in some other table? Like, what if we copied his name into the assignment submissions table in order to avoid another join there? Then we'd have to go update it in that table and any other table where we copied his name, just to try to get a little bit of extra performance out of avoiding a join that's not really costly in the first place. And to make this worse, we would have to do all of these updates inside of a transaction, because what if the power goes out while we're running a whole bunch of commands to update a bunch of rows in various tables? Then only half of them get updated, and you end up with an inconsistent database. And the database administrator, or you as the programmer, you would have to remember what tables need to be updated anytime a student's name changes. You have to document this somewhere, that the name is copied in a whole bunch of different places. So it's a design disaster. It's a terrible design, and it causes these update anomalies that we would need to address. So the main way of fixing this kind of problem, of refining tables that have this kind of problem, is called decomposition. And we've seen this before, I just never really gave it this name. But basically you take one table that has a bunch of columns and you split it into two with some way of getting in between them, some kind of foreign key. So if I had A, B, C, D, I could decompose that into A, B, and B, C, D, or lots of other various potential combinations. That's the basic idea. And you're familiar with this. We've done this, just not formally with this name. So you could go the extreme and just say decompose everything. Make a whole bunch of like 1 or 2 column tables. I could take students and decompose it into just UIDs, and then UID combined with name, and then UID combined with date of birth. But there is absolutely no reason to do that, because all of these things are directly related. Put them all in one table. So, don't decompose if there's no reason to. Do decompose if there is a reason to. So how do we know if there is a reason to or not? You all have probably, hopefully, a pretty good idea of should you decompose a table or not. But today we're going to talk about the formal language and formal way of thinking about this, basically rules. Should you decompose this table or not? So you all have probably come up with good designs for your tables, but let's say you inherited somebody else's design and you want to verify that you don't need to do any decomposition or refinement of those tables. Okay, so how do we know? The basic tool for asking and answering this question is called a functional dependency. So if we can identify functional dependencies and reason about, like, does this functional dependency matter or not, then we can just say, if yes, then we can decompose the table and eliminate these anomalies, where if I change somebody's name, like an update anomaly or an insert anomaly. Okay, so what is a functional dependency? We kind of notate them X, arrow, Y. Basically what this means is that X determines Y. So X and Y are subsets of attributes. So, a single column, a set of columns, some subset of columns on a relation, the same relation. So maybe as an example, X is UID and Y is name from the student's relation. Or X is UID and Y is the combination of name and date of birth. So these are just subsets of fields of columns from some table. Okay, so this is not the full definition. So what is a functional dependency? What this means is if I have a functional dependency from X to Y, remember x and y are columns. If I take any two tuples out of the table and project out x from T1 and project out x from T2, if those are equal, then that means that their y values are also equal. So if I project out the x's and they're equal, then if I project out the y's, they have to be equal, if the functional dependency is true. Okay, so this is for all possible instances of some schema. So whether you have 5 students in the table or 100,000 students in the table, pick any two tuples. This has to hold. Okay, so let's put it in kind of more English terms. A functional dependence xy means basically that x determines y. So take two tuples. If their x values are the same, then their y values have to be the same. So simple example of this. These two tuples can be the same, by the way. They can be, T1 can be equal to T2. So if the UID is the same, then the name has to be the same, right? Somebody with a UID of 1, there is only one person with a UID of 1, which means that is the one person with whatever name they have, Hermione. Okay, but this does not go the other way around. So functional dependency x to y does not imply functional dependency y to x. We'll see, you might be kind of thinking, well, how is that possible? We will see an example of that. Okay, here's a student's table. What are the functional dependencies here? You know that UID is the primary key. So, anyone, give me a functional dependency. Yep.
It should be UID and name, right?
UID and name, yep, there's one. Any others?
UID and date of birth.
UID and date of birth, yes.
Everything depends on UID?
UID to everything, yeah. So I'm abbreviating here now. U for UID, N for name, D for date of birth, G for GPA. So there's a functional dependency from UID to the full set N, D, and G, or any subset of that. So U to D, U to N and G, any combination of the other columns. Yes?
So the other subsets can change, like GPA can change.
So GPA can change, but what?
Sorry, so it doesn't matter if Y can change?
If Y can change,
Like the GPA can be higher or lower, depending on the year.
the GPA can be higher depending on the year of birth?
No, so if I get UID and GPA, then even if GPA can change.
Oh, I see, yes. Yes, so UID determines GPA. GPA does not determine UID. So, yes, a person's GPA can change without their UID changing.
So in the functional dependency, your starting point is always going to be a primary key or a unique key, and then it leads to some subset of things.
Right, so for this particular functional dependency, this is heavily tied to the primary key. This is not really anything new. We know that a primary key uniquely identifies a row. Therefore, the primary key determines everything else in that row. So yes, the question was, do we kind of start with the primary key when looking at functional dependencies? Yeah, those are kind of the obvious ones. But there are, if that was all it was, then this wouldn't really be very interesting. We know all about keys and primary keys. But there are other functional dependencies that don't involve keys. For example, I've added a new column now. I've added a column called funds, like scholarship funds or something. So any other functional dependencies here? Well, you can't really answer that without me telling you what the rules are. we can look at this and see, okay, well, both of the people with a 3.9 have the same funds. The only person with a 4.0 has, the same funds as that only person. But so what I'm not telling you is, yes, we want that to be a rule. We want for the amount of scholarship money somebody receives, we want that to be tied to their GPA. This is like, if that is the case, then we can prove no discrimination, basically. If scholarship funds is strictly related to GPA, then two people with GPA have to receive the same amount of funds. So if I specified that, I would say that there is a functional dependency from GPA to funds, or G to F. And the kind of English version of that is any two students with the same GPA that have the same funding. This is if I wanted to add that additional rule. So this is just a functional dependency that I have said, well, we should have this in our table. Okay. Now, what if I add another student here with these values? So GPA of 3.7, funds of 8K. Does this violate my functional dependency? I see some head shaking. Anyone want? Yeah.
It still holds because it didn't say anything about funds.
Yeah, it does still hold. So do all take any pair of people with the same GPA? Do they have the same funds? Yes. So this is an example where G to F does not mean F to G. Or, X to Y does not mean Y to X. I can have different funding levels for different GPAs, but I cannot have the same GPAs get different funds. Okay. So let's look at this schema. And let's say I do want that restriction, that functional dependency. If this was my table, then this allows for those three anomalies I talked about. The table itself is not preventing me from just going in and changing someone's GPA without also changing their funding. Or it lets me, say I want to insert a new row. How do I know, say I know their GPA, how do I know how much money to give them? I would have to go and find another row with the same GPA in order to figure that out. So I'd have to do another select, be like, okay, we'll go find somebody else with that GPA and then tell me how many funds to give them. Another problem here is, say I delete every single student with a 4.0 for whatever reason, then we've kind of forgot how much money the 4.0 students should get. We've lost that mapping because it's not saved anywhere else. If the student gets deleted, if all such students get deleted, then the mapping is also deleted. Okay. So to fix this, we decompose the relation. We take the functional dependency, so it was GPA to F, GPA to funds. We make a new table that contains those two columns, and then we add a foreign key. We keep a foreign key in the original table that goes to G. Okay, so we have to still have GPA in students, but now we have this other table that maps the funding rates. It's not tied to any particular student. This is just and that's exactly the point, is that this is now non-discriminatory, anyone with a whatever GPA gets whatever funds. Okay? And you make the thing on the left of the functional dependency, you make that the primary key in the new table. Okay, make sense? So this is kind of what I said, we've pretty much been doing this all along, we've just never formally described it.
So is functional dependency just sort of like a sort of theoretical schema thing, and then like foreign keys are how you actually implement it? Is that what you're saying?
Yeah, so a functional dependency is more an abstract, like high-level notion of what the data should mean. And then decomposing the actual tables and using foreign keys and primary keys is how you implement it. Yep.
So does that mean that every time you have a functional dependency, thing that implies the other thing should be a primary key?
So does that mean that every time you have a functional dependency, you should either decompose or the thing on the left of the functional dependency should be the primary key? Kind of. So that kind of depends on how strict you want to be. This is a valid table. So the question is, do I care about this functional dependency enough to do something about it? And there are various sets of rules you can follow. You can say, I want to pick they're called normal forms. You say, I want to follow the first normal form. And then you only follow a certain set of rules. There's second normal form, third normal form. We'll talk about those, and then basically you kind of just say, if you can prove your tables are in a certain normal form, then you can prove certain things about your entire database. Okay, so similar to keys, given a table, we cannot infer its functional dependencies, but given a table and a functional dependency, we can verify if that functional dependency holds. Okay, so given this table and a functional dependency, UID to date of birth, yes, we can prove that. Given this table and no functional dependencies, can we infer what the dependencies are? No. You might say, well, looking at just this information, I would say that there is a functional dependency between name and date of birth. Because everyone with a certain name has a certain date of birth. Because I don't actually have two people with the same name in here. That doesn't mean that it's impossible. So I can't infer that there is a functional dependency from name to date. But I could, if given that functional dependency, I could tell you whether this table violates it or not. Okay. Okay, so kind of back to like the whole design process. We kind of start with the basic idea and then we go to an ER diagram. So this is if you are working through the design from start to finish, rather than if you've inherited a design. We'll get to kind of that. But so here's a simple ER diagram saying, there are professors and departments. A professor works in a department. So subject is the key of a department, like CS or ME or whatever. And then let's say I wanted to add a functional dependency that all professors in a certain department must work in the same building. Okay? So this is kind of, in other words, it's like subject determines building. So S arrow B. How do I fix this ER diagram? Like what I've said so far is the way that we fix these problems is by decomposition. Turns out to fix this functional dependency, or not to fix it, but to make these tables support it, all we do is move building from professors over to departments. Okay, so every single professor should not say what building they work in. Like every single CS professor would then have in their row in the database they would have MEB. That's a lot of redundant information. And if you changed, if we suddenly got a new CS building, you'd have to go and change every record from MEB to whatever the new building is. If instead you put the building on the department, then there's one mapping, one record of that and if you change buildings, you change it in one place, and then magically every professor has changed buildings. So you don't always use decomposition. I didn't have to make a new entity set. I just moved an attribute to another one. But remember, these are not tables. This is an ER diagram, so decomposition doesn't really even apply. We're not dealing with tables, so we can't split a table. Okay? But just kind of a different way to think about it, whether you're dealing with ER or tables. Any questions? Yeah.
How possible is it to say in the future you would come to this company that's built this whole database and they've been putting applications on it for years? So there's numerous applications looking to these tables specifically. Is it even possible to use decomposition at that point without having to go through and fix?
Yeah, so if you have, some database with tons of momentum and tons of applications using it, the problem certainly gets harder. Like if you decide you need to decompose a table, it might be actually no big deal, but depending on like foreign key constraints and everything, it might actually be almost impossible. So that's kind of why it's important to get the design right before you get too heavy into using it. Okay, so now don't start to get alarmed by notation and symbols. We'll kind of walk through all this. But so going back to, let's say you inherited somebody's design and you want to be able to prove certain things about it and know whether you should refine it or not. So dealing with functional dependencies and proving things about them, we have these three things called Armstrong's axioms. So and X and Y are again like subsets of columns from some schema. So reflexivity means if X is a superset of Y, then there is a functional dependency from X to Y. And we'll go through an example of each of these. Augmentation. If there is a functional dependency X to Y, then I can pick some Z and augment both X and Y with that Z. And we get a new functional dependency, XZ to YZ. And transitivity means, what it's always meant. If X determines Y and Y determines Z, then X determines Z. So examples. Reflexivity. If X is a superset of Y, then X determines Y. So let's look at an example. X is name and age. Y is name. If I have somebody's name and age, then I know their name. That's all that's saying. If I have somebody's name and age, then I know their age. Okay, so simpler than the notation makes it look. Augmentation. If I know somebody's UID and their name, so if I'm saying a UID determines a name, then I can also say UID combined with date of birth determines name combined with date of birth. Also kind of not that mind-blowing. But these are like kind of the fundamental properties that we can use to reason about more complex and abstract dependencies. Kind of like the basic rules of algebra. Sometimes the rules are not that mind-blowing, but their applications are very useful. And then transitivity. The example we've actually seen of this was there was a functional dependency from GPA to funds, and there's a functional dependency from UID to everything, so UID to GPA. That means that a UID also determines somebody's funds. All right, so if I go back to this table, can a UID determine how much funds somebody is getting? Yes. Even after decomposing the tables like this. Since UID determines GPA and GPA determines funds, UID determines funds. Okay. Some additional properties that kind of come out of those axioms. If there's a functional dependency from X to the complex Y and Z, then that also implies that there's one from X to Y alone and one from X to Z alone, but not the other way around. So if there is a complex YZ determining X, then you can't say that Y determines Z, and you can't say that you can't say that that is a typo. That should say you can't determine that Y determines X or that Z determines X. Okay. Kind of similarly, if X determines Y and Y determines Z, then X determines the complex Y and Z. So we're not going to make you prove any of this stuff, really. Don't get too hung up on this. This stuff all makes basic sense. If you kind of have to go back and review and like write down a couple little examples, but it's pretty easy to kind of prove it to yourself. Okay, and then finally, there's something called a trivial functional dependency, which is my colors are all messed up here. But, if X determines Y and Y is a subset of X, that's called a trivial functional dependency. So if I have name and GPA determining name, that's trivial. Anything, so X determining X is also trivial. Obviously, anything determines itself. Okay. And then there's this notion of closure. Okay, so if I have some known functional dependency or dependencies, F. So F is a set of known functional dependencies. Those are only the known ones. They're using those Armstrong's axioms. There are potentially a lot more functional dependencies that you can prove. And that's called the closure of F. So given F and the simple logical rules, this notation F plus, that's called the closure of F. That is all of the functional dependencies you can prove given some small set of known functional dependencies. So for example, if I know that UID determines everything and GPA determines funds, there are other functional dependencies I could make out of that. That's called the closure. Okay, so that's kind of the basic, formal language. We will use that to discuss, like, how do we use this? What can we do about it? How should we refine our tables? So let's take our 5-minute break now.